Hello everyone, on today's video we will go through the space-time and the Damkohler number. We'll start off with the space-time. The space-time is basically the time required for one reactor volume to react. And it's symbolized with tau, which equals to volume of the reactor divided by the volumetric flow rate. I know in the previous videos for the volumetric flow rate I've used small v, but to avoid any misunderstandings I've used q for now for this video. So the space-time we said is the time of one reactor volume to react, and the Damkohler number is a unitless number which is used to study the effects of the physical parameters on the conversion rate. Physical parameters, I mean, such as temperature, volume of the reactor, and volumetric flow rate. And I'll show you how to derive the Damkohler number, which is the space-time times k, which is the rate of reaction constant, which is a function of temperature. So to start off with the derivation of the Damkohler number, we'll use the space-time. Let's assume for our example a CSTR reactor. Okay. In the previous video titled conversion in CSTR, we found the volume of a CSTR in terms of conversion to equal negative FA naught times X divided by rate of reaction, which if we go to the previous notes, it's this one right here. Okay, so we can go ahead and substitute that into our space-time equation. Tau equals negative FA naught X divided by rate of reaction. That's your V, and divided by Q. Okay. Now we know that concentration equals mole flow rate divided by volumetric flow rate. Therefore, FA equals CA times Q. We're going to substitute that here in order to get rid of the Q. So space-time equals negative CA naught times Q times X divided by RA times Q. That way we can cancel the Q and we'll be left with space-time equals negative CA naught X divided by the rate of reaction. For our rate of reaction, we'll use a first order rate of reaction for this example, which equals to negative K times CA. Negative because A is a reactant which is being consumed. Also for the CA, the concentration, we'll write that in terms of conversion, X. Therefore, the space-time equals negative CA naught X divided by negative K CA naught times 1 minus X. Therefore, we can cancel the initial concentration. Therefore, we'll be left with space-time equals, we can also cancel the signs. We'll be left with X divided by K times 1 minus X. We'll move this K to the left side. That way, tau times K will equals our Damkohler number, which equals to X divided by 1 minus X. There's our Damkohler number. We can also go a step further and substitute this tau, the space-time, with volume divided by volumetric flow rate. Why? Because space-time equals volume divided by volumetric flow rate. Okay, we'll times it by K equals X divided by 1 minus X. That also is our Damkohler number. Okay. Which, as I said at the beginning, is the Damkohler number is a dimensionless number used to study the effects of physical properties such as temperature, which is K is a function of temperature, volume of the reactor, and volumetric flow rate versus the end result, which is the conversion. That's it for this video. And if, for example, there will be small changes, for example, if you decided to go with a second order rate of reaction, it's not that complicated. But we'll do that in another video. But that's it for now, and have a good day.